Good morning everyone. Today I am going to explain digital to analog conversion method by using of R2 to R ladder network. So before going to start today's class, we are already completed about digital to analog converter definition and one type of digital to analog converter is also completed. In digital to analog converters, we are giving the digital input and we are getting the analog output. The input is in the form of digital, that is nothing but it is a binary values either 0 or 1. The analog output will be related to either voltage or current. So digital to analog converter, another name is called DAC or D2A converter. So by using of digital to analog conversion, we have two methods. Converting from digital to analog, we have two methods. First one is the binary weighted resistor and second one is the R2 to R ladder DAC. In binary weighted resistor type, so the name itself, it contains the binary values. The binary values are depends on the weights of resistors, that is nothing but R2, R4, R8. These are completed in previous class only. So binary weighted resistor type is the first type. So binary weighted resistor have some disadvantages. So by overcoming the binary weighted resistor disadvantages, we have another method is used. The another method, the name itself, R2 to R ladder network. The main problem in binary weighted method is, so the circuit completely depends on the resistance values only. If the number of resistors are increased, the circuit complexity will be more, and at the same time tolerance problems also, the tolerance problem, number of resistors are increased, the tolerance problem also increased. So first, the main advantage of binary weighted is simple circuit, first basic method. But the main disadvantage is the circuit completely depends on the only weights of resistors. So that's why number of resistors are increased, circuit complexity will be more. So overcome the disadvantages in binary weighted resistor, we have another method, that is R2 to R ladder network. So today I am going to explain R2 to R ladder network. So R2 to R ladder network is also one type of digital to analog conversion method. This is the most popular type of digital to analog converter method. Next, it uses a ladder network, it containing series parallel combination of two resistors. The two resistor values are Rn 2R. So it uses a series parallel combination. The Rn, the complete circuit designing by using of only the two resistors. The two resistors are Rn 2R. The Rn 2R will be arranged in the manner of series and parallel combinations. Next, the main advantage of ladder type resistor network, it requires only the values of resistors R and 2R. Next, hence the name of the network is called R2 2R network. Why we are calling it is R2 2R is nothing but here we are using only the two resistors called R and 2R, and we are arranging the R and 2R resistors in a series parallel combination. So the circuit requires only less components, that's the circuit requires only the R2R resistor, and the R2R will be arranged in simple manner, that is nothing series parallel combination. Next, R2 to R ladder network, to overcome the difficulties in weighted resistor method of digital to analog conversion. So by using of R2 to R ladder network resistor type network, so the overcoming the difficulties in weighted resistor, so next we can choose the R2 to R ladder type resistor network. Next, this method eliminates the range problems because here we are using only the two resistance values. The two resistance values are needed. The resistor in this type of converter in the same IC chip, hence the tolerance problems also minimized. The resistor converter in the same IC chip, same integrated circuit, so the tolerance problems also minimized. Next, R2 to R digital to analog converter, which requires only the two precision resistances. The R2 to R ladder network uses just two resistor values, one which is the base value R and other one is the twice value. The twice value is nothing but 2R. So here we are using Rn 2R. R is a base value and another one is the twice value is nothing but 2R. Rn 2R of the first resistor number matter how many bits are used make up the ladder network. And the name it implies ladder description comes from the ladder like configuration of resistors are used within a network. So here we are using ladder type of resistor, ladder like construction, that the resistors R and 2R will be arranged in the manner of ladder shape. The ladder like configuration of resistors are used within the network. A R2 2R resistive ladder network, it provides a simple means of converting digital into analog, digital voltage signals into equivalent analog output. So the digital values will be converted into analog output. Here we are giving the digital input. The digital input will be converted into analog output. The analog output is in the form of either voltage or current. So this is the R2 2R ladder D2A converter circuit. Here each bit is corresponds to a switch. This is the different bits. This is the 4-bit converter. Here we have taken the bits from bit 0, bit 1, bit 2, bit 3. These are the 4-bit converter. Next, we are arranging the resistors in a R and 2R series parallel combination. This is the first resistor R, 2R, R, 2R, R, 2R. So arranging the resistors in a series parallel combination, and the output will be given to inverting terminal of op amp. The resistor, the output will be, bit output will be given to inverting terminal of op amp. So the op amp, it consists of mainly two inputs. One is the inverting input and second one is the non-inverting input. And the R, here the R is the feedbacking resistor and the last one is the V out. V out is the output. So the V out, it indicating the analog output voltage. So here each bit is corresponds to a switch. If the bit is high, the corresponding switch is connected to the inverting input of op amp. When the bit is high, the bits is nothing but here the bits from 0 to 3, bit 1, bit 0, bit 1, bit 2, bit 3. If the bit is high, the corresponding switch is connected to inverting terminal of op amp. Or if the bit is low, high indicating means binary 1 or low indicating means binary 0. If the bit position indicating low, so the corresponding switch is connected to ground. So whenever the binary 1 indicating, the switch position is 1 indicating, it will be connected to inverting terminal of op amp. Whenever it connected to 0, that is nothing but bit is 0, it is connected to ground case. So here it requires only two precision resistor values R and 2R. So this is also R2 2R ladder DAC. So here the bits starting from LSBT to MSB. LSB is nothing but least significant bit and MSB stands for most significant bit. So we are taking 4-bit converter and it will be starts from B0 to B1, B2, B3. If at all B0 is called LSB bit and B3 is called MSB bit. Least significant bit is B0 and most significant bit is B3. Next, R2 2R ladder digital to analog converter is a 4-bit R2 2R ladder type. Digital to analog converter is the most popular type of DAC. It uses a ladder network containing of series parallel combinations of values R and 2R. Next, it is easily scalable to any desired number of bits. It uses only two values of resistors, which make for easy and accurate fabrication and integration purpose. The two values of resistors we are arranged. So that's why the circuit designing is easy and it also accurate fabrication of integration. The output impedance is equals to R regardless the number of bits and simplifying the filtering further analog signal processing circuit design also. So this is the circuit R2 2R ladder network. Here we are using R and 2R combination. The main advantage of this circuit is nothing but it uses only R and 2R. Hence the name it is called R2 2R ladder network. So the circuit diagram of R2 2R ladder network, it consisting of the resistors R and 2R. We are arranging the R and 2R is in a series parallel manner. R and 2R is in a series parallel combination. Next, Here V reference is the reference voltages, voltage switches with a V reference, voltage or reference voltage. Next S0, S1, S2, S3. These four are the four switches. Thus S0 is called least significant bit and S3 is called most significant bit. Next this is all called resistive summing network. So R2R combination is called resistive summing network. The resistive summing network will be connected with voltage reference switch, VR voltage reference. Next, the output will be connected to op-amp inverting terminal. The op-amp inverting terminal will be connected to outputs of bits, output of S0, S2, S3 combinations, and RF is the feedbacking resistance, and the non-inverting terminal will be connected to ground case, and the V0 is nothing but output voltage. So here the op-amp it works as a amplifier, operational amplifier. So this is the circuit diagram. The circuit diagram itself consists of reference voltage. The reference voltage will be connected with switches. That's why voltage switches with V reference, and the reference voltage it starts from next is the switches, it starts from least significant bit to most significant bit. The least significant bit is called S0 and the most significant bit is called S3. And the resistors here we are using R and 2R. The R and 2R resistors are we are arranged in a simple form like series parallel combination. And next one is the R and 2R resistors are work as a resistive summing network. Next, the output of resistive summing network is given to op-amp. Op-amp is called operational amplifier. The output will be connected to inverting terminal of op-amp and non-inverting terminal will be connected to ground case. Here the op-amp it uses negative feedbacking. Feedbacking is nothing but by using of RF feedback. So feedbacking is nothing but a connection, direct connection from output to input. Here we are using the feedbacking purpose resistor. The feedback resistor is called RF. This is about the designing of circuit. Designing means simple designing. It uses only two resistor combinations and switches, and only one op-amp is used. If the input is binary input is 1, if the input is binary input is 1, so the bit is, whenever the bit is high, that it will be connected to op-amp. The resistive network will be connected to op-amp inverting terminal. Wherever the bit is low, that is nothing but the switch position whenever it indicating 1, so the output will be connected to op-amp inverting terminal. If the switch position is indicated to 0 position, so the output is connected to ground case. This is the ground terminal. So the based on bit positions we connected either op-amp or it will be connected to ground case. If the position is indicating 1, that is nothing but binary high value, the output will be connected to op-amp, and then we are getting the output is in the form of analog. So the op-amp output section is in analog only. If at all the binary bit is input binary bit is 0 or low value, so it will be connected to ground case. So working of R2 2R ladder network is nothing but the operation of the circuit can be simplified by using of Thevenin's theorem. So by using simplifying Thevenin's theorem, that is nothing but each and every time we are calculating the Thevenin's equivalent voltage, and next we are simplifying the circuit by using only Thevenin's theorem. The simplifying is nothing but first we are simplifying the R and 2R combinations. Next we will obtain the equivalent voltage. Whenever we are simplifying the R2R combinations, we are obtaining the equivalent voltages. So let us assume the digital inputs S3, S2, S1, S0 as 0, 0, 0, 0, 1. That is nothing but S0 is equals to 1, S1 is equals to 0, S2 is equals to 0, S3 is equals to 0. That is nothing but S0 is the least significant bit. So we are assuming the bits from least significant to most significant bit. First the least significant bit is 1 and the remaining bits are zeros. So that is nothing but least significant bit is S0 is equals to 1 and the remaining bits, binary bits are S1, S2, S3. S3 is the most significant and S1, S2 are the binary inputs. So the all are equals to 0. So by this application, by the applications of Thevenin's theorem, the respective network is the LSB bit is assumed 1 and the equivalent voltage is VR by 2 power 4. So, the specifications of D2A converter using Thevenin's theorem. So, first we are specifying the first binary 1 and that is nothing but LSB is 1, the remaining bits are 0. So, the remaining bits are 0, the Thevenin's equivalent voltage is nothing but VR by 2 power 4. So, first this is the VR, VR is the V reference voltage, these are the R and 2R combinations, this is the LSB bit. Here this is we are taken LSB bit and next one is the MSB bit. So, this is the R to R combinations. Next one is the next position. Next VR by 2 1. Next VR by 2 square. First one is the VR V reference voltage. Next, whenever we are simplifying this equation, first we are getting the voltage V reference level. Next VR by 2 power 1. Next we are simplifying the another R and 2R combinations. The reference voltage is nothing but VR by 2 power 1. So, next time, so malli again we are simplifying the R to R combinations. The reference voltage is VR by 2 square and again we are simplifying the R to R combinations, that is nothing but by applying Thevenin's theorem we are simplifying the Thevenin's equivalent voltage is VR by 2 cube. Next one is the VR by 2 power 4 and the last one is the VR by 2 power 4 and this is the 3R, R and 2R combinations. Here the R and 2R resistors are in series, the R and 2R resistors are simplified by 3R, that these are two series resistors, the value is nothing but 3R resistance. So, working of R2 2R ladder network is nothing but, so it will be worked based on the Thevenin's theorem. So, based on Thevenin's theorem only it will be working. Next, similarly the digital inputs of 0010, 0100 and 1000 are the equivalent voltages and the equivalent voltages by 0010 the Thevenin's voltage is VR by 2 power 3. Whenever we are taking the inputs as 0100, that is nothing but by S1 is equals to 1. Next to that time the voltage is equals to VR by 2 square. Whenever MSB bit is equals to 1, that is nothing but VR by 2 power 1. So, first of all LSB bit is 1, then afterwards S1 switch is 1, next to S2 is equals to 1 and the last time is S3 is equals to, S3 is nothing but most significant bit is 1. Whenever S0 is equals to 1, the reference voltage is nothing but VR by 2 power 4. Next, whenever S1 is equals to 1, the reference voltage or the Thevenin's equivalent voltage is represented as VR by 2 cube. Next, S2 is equals to 1, it will be represented as VR by 2 square and VR by, next one is the third case, that is nothing but MSB is equals to 1, that is nothing but VR by 2 power 1 respectively. The Thevenin, that is the equivalent resistors in a 3R in each case. From the circuit the output analog voltage can be determined. So, the analog voltage can be determined, each time equivalent resistance is 3R and next the output analog voltages can be determined. Next, then the V0 is given by V0 is equals to RF by V0 is equals to RF into VR S0 by 3R into 2 power 4 plus RF into VR S1 by 3R into 2 power 3. Next, plus RF into VR is nothing but V reference voltage, S2 is nothing but switch 2. First case RF by VR, so VR is reference voltage and switch S0 and it by 3R into 2 power 4 plus whenever S1 is equals to 1, that is nothing but RF into VR S1 by 3R into 2 cube plus whenever switch 2 is equals to 1, VR by RF into VR S2 by 3R plus 2 square plus RF into whenever MSB bit is equals to 1, RF into VR S3 is nothing but MSB bit is equals to 1 by 3R into 2 power 1. So, that is nothing but we are simplifying the above equation, then we are getting the V0 is equals to RF into VR by 3, RF into VR by 3R into 2 power 4, again 2 cube into S cube plus 2 square into S square, 2 square into S2 plus 2 power 1 into S1, next 2 power 0 into S naught. So, where the minus sign indicates phase inversion. So, the complete circuit by using of simplifying the R2 2R ladder network is used for simplifying the Thevenin's theorem. So, what is the Thevenin's theorem? The Thevenin's theorem, it states that it is impossible to simplify any linear circuit to how much complete it equivalent. Just a single voltage series connected to resistive load. The series resistor is connected to the load. So, why we are using Thevenin's theorem is nothing but the Thevenin's theorem, it provides an easy method for analyzing power circuits, which is typically has a load changes value during the analysis process. The theorem, it provides the efficient way to calculate voltage and current flowing to the load without having no recalculate your entire circuit over again. So, Thevenin's theorem statement is nothing but the Thevenin's theorem, it states that is, it is possible to simplify any linear circuit no matter how complex an equivalent circuit with a single voltage source and single resistance. That is nothing but the total circuit will be replaced by a single resistance and single load. The total circuit is simplified by using of Thevenin's equivalent voltage and Thevenin's equivalent resistance. So, Thevenin's theorem, how can we can apply it? That is nothing but the Thevenin's theorem applications is, first open a two terminals, remove the load circuit between which you want to fill the Thevenin's equivalent, determine the Thevenins across the two open terminals. First of all, we are removing load in the circuit, and then after we are applying Thevenin's voltage, determine the voltage across the open terminals, and at the same time determine the resistance. Thevenin's voltage is called V Thevenin's, Thevenin's resistance is called R Thevenin's. So, Thevenin's resistance between the two open terminals with all sources are replaced with internal resistance. So, by using this we can calculate the circuit diagram. By using this expression we can, in Thevenin's theorem, the statement of Thevenin's theorem is nothing but all the voltage sources and all the resistance are replaced by a single voltage source and single resistance. The single voltage source is called V Thevenin's and single resistance is called R Thevenin's. So, the Thevenin's theorem is used for the simplifying, used for simplifying purpose. That is nothing but used for calculating the voltage and resistance. It is a simple method for calculating voltage and resistance. So, the Thevenin's theorem statement already in network analysis subject. So, the network analysis subject is in your third semester only. Just here only the Thevenin's theorem, by using the circuit will be described by using of Thevenin's theorem. No statement is here, just I am describing about statement. Thevenin's theorem is nothing but all the voltage and current, all the voltage sources and resistance sources are replaced by a single terminal. So, Thevenin's, by using of Thevenin's theorem, then the V naught is calculated. V naught is equals to RF into VR S naught by 3 power 4 into 2 power 4 plus RF into VR S1 by 3R into 2 cube plus RF into VR S2 by 3R into 2 square plus RF VR into S3 by 3R into 2 power 1. V naught is equals to RF into VR by 3R plus into RF into VR by 3 power 4, just we are common terminating terms. Next, we can common the RF by VR into RF VR by 3R. Then afterwards we have 2 power 4 into S power 4 plus 2 power 4 into S cube plus 2 cube into S square plus 2 power 1 into S naught plus 2 power 0 into S naught, where minus sign indicating the phase inversion. Here, by using above expression, the analog output voltage is determined for various switch positions in the digital input. So, advantages of R2 2R ladder DAC is nothing but easy to build accurately. Only 2 precision metal film resistors are required. Number of bits can be expanded by adding more sections of same R2 2R values. The 2 precision resistors are used and number of bits can be expanded by R2 2R values. And inverted R2 2R ladder DAC, node voltages remain constant with changing the input binary words. The advantages of R2 2R ladder DAC is nothing but it uses only two resistor values R and 2R. It uses only the two resistor values R and 2R, and the cost is low because the two values are used. Next, the tolerance and range problems are minimized because only the two resistors are used. Next, disadvantages of R2 2R ladder DAC is nothing but lower conversion speed than binary weighted digital to analog converter, and propagation delay is also more. Advantages is nothing but two resistors are used. Next, cost is low and the tolerance problems are minimized, but the main disadvantage is propagation delay. Just here using only Thevenin's theorem. The Thevenin's theorem is nothing but all the voltage and resistances are replaced by single voltage source and single resistance. So the single voltage and single resistance are used for simplifying this circuit. By using of Thevenin's theorem, we can simplify the circuit. We can simplify the total circuit, and next we are find outing the equivalent voltages. R2 2R ladder digital to analog converter, only two resistor values are used. It does not need a precision resistors and binary weighted digital to analog converters, and it is cheap, easy to manufacture and easier to response time, faster response time. The main disadvantages is nothing but slower conversion rate and more confusing analysis. These are the some examples or some multiple choice questions related to R2 2R ladder network. First question. So first, find the analog output of R2 2R ladder network. So the binary bits is nothing but binary bit B0, B2, B2, B1, B0 is nothing but 1000. The circuit diagram of 3-bit R2 2R ladder is nothing but B0, B1, B2, B3 is applied to the figure. First, the resistor values of the point A2 with respect to ground. So we can replace the entire network using of a single resistor using of 2R resistor. The simplified diagram is this. So in the above circuit, the exist series resistor combinations are two resistors. It will be replaced by a single resistor. The final circuit diagram is shown in the figure. So this is the final circuit. So first find out in the R2 2R ladder network. So find the analog output voltage. Let us find the analog output voltage of R2 2R ladder. This is the R2 2R ladder network. So this R2 2R ladder network, the binary input is a combination of, this is 4-bit R2 2R ladder network. The binary inputs is nothing but B0, B1, B2, B0, B1, B2 are the 1000, and the 3-bit one. The 3-bit R2 2R ladder is nothing but the binary inputs are B0, first one, B1, B2. So B0, B1, B2 is nothing but 100 is applied. So this is the 3-bit code. The 100 is applied to the figure. First, by using of Thevenin's theorem, we can simplify the circuit. The three binary bits B0, B1, B2 inputs are 100, B0 in. So first it will be replaced by a Thevenin's equivalent circuit. That is nothing but the resistors of a left point A. The resistors across left point A with respective to ground. So we can replace the entire network first with a single resistor having 2R ohms. This is the simplified diagram. The simplified diagram, it consists of V0 is the output voltage and the 2R is the feedbacking resistance, R is the inverting input resistance, and that the total entire R and 2R resistors are replaced by 2R resistor. Next, the above circuit, there exists a series combination of two resistors. It will be replaced by the combination of single resistor. The two series resistors are replaced by a single resistor. Next, the final circuit diagram after simplification. This is the final circuit diagram. The final circuit diagram, it contains the input voltage of minus VR by 2. That is nothing but here the MSB bit is 1. Now the above circuit is look like an inverting amplifier. The input voltage of minus VR by 2 volts is the input resistance is 2R by ohm and the feedbacking resistance is 2R ohm. The output voltage is nothing but the inverting input terminal gain is equals to V0 by V1 is equals to minus RF by R1, the gain value. So the circuit is like inverting input terminal. So here the input voltage is nothing but minus VR by 2 volts. V naught by Vi is equals to minus Rf by R1. V naught is equals to minus Rf by R1 into Vi. Here the Vi value is what? Vr by 2. V naught is equals to minus Rf by minus Rf is equals to Rf is nothing but feedbacking resistance. The feedbacking resistance value here is the 2R value and minus Rf by R1. R1 is the input resistance. Input resistance is 2R. So, this is the feedbacking resistor minus 2R. This is the input resistance R1. Next, Rf by R1. V naught by Vi is equals to minus Rf by R1. V naught is equals to minus Rf by R1 into Vi. Vi is nothing but minus Vr by 2. So, V naught is equals to minus Rf is equals to the minus Rf value here is the 2R. Minus 2R, Rf place in place of Rf we have 2R value, R1 value is the 2R resistance and the input resistance minus Vr by 2. So, just we can substitute these in the output voltage. So, output voltage of inverting terminal V0 is equals to minus Rf by R1 into Vi, that is nothing but V0 is equals to Vr by 2. So, therefore, the output voltage of 3-bit R2 2R ladder DAC is the Vr by 2 volts for a binary input of 1 0 0 combination B0 B1 B2. Next, second question. This is the first example and this is the example related to binary R2 2R ladder network, and second question is the multiple choice questions. So, the inverted R2 2R ladder can be also operated in inverted mode, current mode, voltage mode and non-inverted mode. So, the already it name indicates inverted R2 2R ladder. So, the inverted R2 2R ladder can be operated in a current mode. How we can tell current mode is nothing but the inverted R2 2R ladder DAC circuit works on the principle of summing current. So, it will be work on the principle of summing current is nothing but therefore, it's said to be operated in a current mode. So, it will be work on the current mode. Second, next question, calculate the value of LSB and MSB of a 12-bit DAC of 12-bit DAC for 10 volts. Calculate the LSB and MSB. So, LSB least significant bit and most significant bit of 12-bit digital to analog converter for the output of 10 volts. So, how we can calculate means LSB is equals to 1 by 2 power n. 1 by 2 power n is nothing but 1 by here is a 2 power n is nothing but n is nothing but 12 bits. So, the number of bits is 12. 1 by 2 power 12 is equals to 1 by 2 power 12 is nothing but 4096. So, for it is a 10 volts range. So, the 10 volts range is equals to LSB is equals to 10 volts by 4096. 4096 is nothing but 2 power 12 value. So, LSB is equals to 10 volts by 4096, that indicates 2.4 millivolts. Same, whereas MSB is equals to, MSB is nothing but 1 by 2 of full scale value. 1 by 2 of full scale is nothing but 10 volts. So, 1 by 2 of 10 is nothing but 5 volts. So, for LSB and MSB of 12-bit digital to analog converter, the LSB is nothing but 1 by 2 power 12, that is nothing but 1 by 4096, and for it is a 10 volts range, 10 by 4096 indicating the LSB value is 2.4 millivolts and the MSB value is nothing but 1 by 2 of full scale. So, 1 by 2 into 10 volts is nothing but 5 volts. Next, last question, the basic step of 8-bit digital to analog converter is 12.4 millivolts if the binary input is all zeros represents as a 0 volts. Determine the output input is, determine the output if the input is 1011041111. First, the basic step of 8-bit DAC and digital to analog converter value is 12.4 volts. If the binary inputs are all 0. So, then binary inputs are all 0, it represents only 0 value. So, determine the output. So, determine the output if the binary input is 101, 101, 1111. So, first the values will be 0, then the output, then next the input will be, first the input will be 0, then output also 0, next the input is represented as 10, 110, 1111, then calculate the output. So, first the output voltage for the input is 10, 110, 111, it indicates 12.4 millivolts into 1 into 2 power 7 plus 0 into 2 power 6 plus 1 into 2 power 5 plus 1 into 2 power 4, arranging in a decreasing order. 1 into 2 power 7 plus 0 into 2 power 6 plus 1 into 2 power 5, 2 power n to 2 power 0. 2 power n is nothing but here the 8-bit converter, 2 power n minus 1 to 2 power 0, that is nothing but 1 into 2 power 7 plus 0 into 2 power 6 plus 1 into 2 power 5 plus 1 into 2 power 4 plus 0 into 2 power 3 plus 1 into 2 square plus 1 into 2 power 1 plus 1 into 2 power 0, that is nothing but 12.4 into 1 into 2 power 7 is nothing but the 2 power 7 value is 128 plus 2 power 6 is 36, 2 power next 64 plus 2 power 6 is 64 plus 2 power 5 is 32, next 2 power 4 is 16, 2 cube is 8, 2 square is next 2 square 2 power 6 is equals to 64. Why we can take 64 value as 0 is nothing but here we are multiplying 0 into 2 power 6 is nothing but the value will be 0. Next 1 into 2 power 5 is 32. Next 1 into 2 power 4 is 16 plus 0 into 2 cube. The already 2 cube value is 8 but 8 into 0 is 0. Then afterwards 1 into 2 square is 4 and 1 into 2 power 1 is nothing but 2 and the 2 power 0 value is 1, 1 into 1, 1. So the total value is 2 power 12.4 millivolts into 183, that is nothing but 2.27 volts. So how we can calculate is nothing but first the input voltage will be multiplied with number of bits, that is nothing but 1 into 2 power 7, 1 into 0 into 2 power 6, then finally we are getting the 2.27 volts. So this is the R2 2R. So R2 2R is nothing but the R and 2R combination. It is a ladder networking type. The construction is ladder networking. Ladder type, it requires only the two resistors R and 2R. Next, the R2 2R is just it eliminating the problems in binary weighted resistor. Next, it is the main advantage. Tolerance problems also minimized and simple circuit, cost effective, less cost, only the resistor values R and 2R is needed. Next, they are arranging in the R and 2R in a only ladder network, resistive ladder type, that is nothing but arranging in a ladder shape and the output will be given to op amp. If the bits are high, the output will be connected to op amp, otherwise bits are low, output will be connected to ground case. This is the R2 2R ladder network. So it will be consisting of V reference voltage and followed by number of switches. This is the 4-bit converter consisting of 4 switches. The 4 switches are arranged in the manner from LSB to MSB. LSB is nothing but least significant and MSB is most significant, and R and 2R resistors are arranged in the manner of series and parallel combinations. But the simplifying the above circuit by using of Thevenin's theorem. The Thevenin's theorem, it indicates the total circuit will be replaced, the total voltage sources will be replaced by a single voltage source and the total resistances are replaced by a single resistance. The total voltage sources is replaced by single voltage is called V Thevenins and total resistances are replaced by R Thevenins. So by we can replace means simplifying the circuit simplification purpose, we can simplify all voltages at the nodes are replaced by a single voltage source, or we can consider as a single voltage source and all the resistances are replaced by single resistances. So if all the circuits are, and also it can eliminate the load, that is nothing but the circuit is in a open state configuration, that is nothing but there is no load, that all voltage sources are replaced by single voltage source and all the resistances are replaced by single resistance in Thevenin's theorem. The circuit is in a open state configuration, that is nothing but no load voltage. So here the binary input. So first we are taking one example. The example consisting of the digital inputs are from binary 0 to first LSB bit is 1 and the remaining bits are 0, that is nothing but least significant bit is 1 and the remaining bits are 0. Then the equivalent voltage is VR by 2 power R, 2 power 4. Next, same in the same manner second switch is 1, that is nothing but S1 is 1 and the remaining bits are 0. The equivalent voltage is VR by 2 cube. Next, if the third switch is on, that is nothing but S2 is on, the binary value, the Thevenin's value is VR by 2 square and the finally MSB bit is 1, then VR by 2. This is the VR, next VR by 2 power 1, next VR by 2 square, 2 cube, VR by 2 power 4. The VR by 2 power 4 is nothing but in this case LSB bit is equals to 1 and the remaining all other bits are 0. VR by 2 power 4. Here R and 2R. R and 2R is nothing but the two resistors are in a series. That's why we are getting the 3R value. Next here the VR by 2 cube is nothing but S2 switch is connected. That's why. So it will be indicate, sorry, S1 switch is connected. So it will be the equivalent voltage is VR by 2 cube. Next, this is the R and 2R resistor combinations. Next here the 2 square is nothing but S2 switch is connected. Here the S1 switch is connected. So then that it is the output. In the output first we are common the values RF by VR. So then we are getting the RF by VR, RF into VR by 3R is equals to RF into VR by 3R into 2 power 4 into S cube plus 2S square S1 S0. So where the minus sign indicating phase inversion. Why we are getting minus sign is nothing but we are connecting the terminals into inverting terminal of op-amp. It is a simple circuit, easy construction, delay is more, but the disadvantage is delay is more. This is the examples related to R2 to R ladder network. These are the some multiple choice questions. R2 to R is working on the current mode, and the next 12-bit calculations purpose. This is the two examples. Thank you all.